Alright, so welcome back to the seventh and the final part of the third week on dynamic programming algorithms. And in this video, I want to introduce you to a problem called the maximum independent set problem. And we are going to be looking at this problem on the class of graphs which are called trees. Okay, so it turns out that the independent set problem is a very hard problem in general, and again it's something that we will revisit when we get to week 6 or so. But when we look at it constrained to trees, it turns out that it becomes much easier to deal with. But before I give you the formal definitions, let me try to motivate this problem through a puzzle. So imagine that you want to invite people at a company to a party, and you have one rule, which is that you should not invite a person and their manager together. So an employee and their manager should not be invited together. The assumption is that when this happens, the party gets awkward for both of them. So it's okay if you invite the manager's manager, because the employee probably does not have a lot of direct contact with them, but you don't want to invite the immediate managers if you're inviting them. Or you could invite the manager, not invite the employee, but basically avoid inviting them together. Now, let's say that each employee has a fun factor associated with them, which is basically how much life they bring to the party. It's some sort of a quantification of that. So imagine giving all the employees points on a scale of 1 to 10 or something based on how much life they're going to add to the party if they were to come. And what we want to do, of course, is we want to maximize for fun. We want to organize a party that's as fun as it can be, but of course it's subject to this constraint here. So let's look at an example. So normally corporate hierarchies look like trees. You must have seen these organizational charts, which are very tree-like. So you probably have some sort of a CEO chap on the top, and then there's like a bunch of people who report to him. And I did mean to say him or her. And well, this goes on, right? So you can have an organizational chart that goes down fairly deep. But I'm going to stop here just so that I find space to fit everything in. And now let's put down some fun factors. So let's say these are the fun factors that are associated with all of these employees here, who happen to be nameless and faceless at the moment, but we do know how much fun they're going to bring to our party. And now if you had to find a subset of people to invite who maximize for fun, remember this may not actually be the largest set of people that you can invite. It's possible that a smaller set of people are more fun compared to a larger set, just because of the way the numbers are. But here are some examples of people that you cannot invite simultaneously, just to clarify what I meant by our constraint earlier. So for example, you cannot invite the CEO along with any of their direct reports. So this would not be a valid invitee list. Similarly, you cannot invite these guys together, but you can invite these people together. That's not going to be a problem. Okay, so let's maybe do a couple of examples of invitee lists that would work. So for instance, we could just invite everybody here, and that would not be a problem, along with the CEO, right? The total fun that we obtain by doing this is going to be the sum of all of these numbers here. So it's going to be 5 plus 9 plus 7 plus 1 plus 6 plus 10 plus 5 plus 1 plus 2 plus 3. And I hope you worked that out because I didn't. But what I want to know here, and this is why the exact number is not so important, but I want to know if you think that there's a different party here that could be even more fun. Well, in this case, it seems like that's a little bit tricky because we seem to have accumulated quite a bit of fun already. But let's experiment with seeing what happens if we also invite the person who has a fun factor of 9 here, because that sounds like a person who is a lot of fun. But in the bargain of inviting this person, you would have to let go of both the CEO as well as these 3 people here. So you gained 9, but you lost 5 plus 1 plus 2 plus 3. And this I can calculate and see is more than 9. So that was not a very clever move. However, if these fun factors were a little bit smaller, like 1, 1, and 1, then this exchange would have made sense because you gain 9 and you only lose 8. So this new party is more fun than the one before. You can continue staring at these numbers or come up with your own example and see if you can find out what party would be the most fun. And while you're at it, while you're hacking these examples, I would also like you to think about perhaps a solution for actually finding the most fun invitee list algorithmically, right? In the meantime, let me set you up with some terminology so that you know what this problem is officially called outside the party puzzle. So you've probably already encountered trees. In fact, we just talked about binary search trees in the previous video, but those were binary trees and they had, keys associated with them, and it's a slightly different setting. In general, in graph theory, a tree is simply a connected graph that does not have any cycles. And the other term that we have in the name of the problem is independent set. And what is an independent set? Well, it's a subset of vertices in a graph G that has no edges involved in it. So it's a subset of vertices such that for any pair of vertices in that subset, the pair does not have an edge going between them. Right? So here I'm implicitly assuming that we are dealing with a graph G whose vertex set is V and edge set is E. Let me give you a couple of examples of independent sets on general graphs, not necessarily trees. So here's a collection of vertices that forms an independent set, and notice that I really cannot add anything to this set without violating the definition. So if I add this, I'd have this edge here. If I added this, I'd have these edges here, and so on. So I can't really do much better than this if I'm committed to picking these vertices in the independent set. But of course, there could be a larger independent set. So for example, I could swap out that vertex with these two, and I still have an independent set, but it's one bigger from what I had last time. Can you get an even bigger independent set? I'll leave that for you to think about. But the computational problem that's associated with the concept of an independent set is what's called the maximum independent set problem, where the input is a graph G and a target K, and the output is yes if G has an independent set of size at least K. And of course, it's understood to be no otherwise. The optimization problem is just find me a largest subset of vertices that form an independent set. So in general, it turns out that this independent set problem is quite hard, and we will in fact revisit it when we get to week 6. But if the graph was not just an arbitrary graph, but it happened to be a tree, then it turns out that you can solve the maximum independent set problem in polynomial time, and that's exactly what we are going to do. If you go back and think about the party problem, that's just really asking for a maximum independent set. In fact, here we are asking for a maximum weight independent set, which is a natural extension of this problem. So basically you're given a vertex weighted graph, and the weight of an independent set is simply the sum of the weights of all the vertices in it, and you're looking to find a max weight independent set. So I trust that you can make those translations naturally, so I'm not going to write them down. So now let's come back to actually thinking about how we can solve this problem by coming up with an appropriate recurrence. So with trees, it's really convenient often to just identify an arbitrary vertex, call it the root, and all the vertices adjacent to the root now become its children, and so on. I mean, unlike BSTs, now there is no constraint on how many children you can have. This is a general tree. And now our dynamic programming approach is going to very naturally follow the recursive structure that the tree inherently has. Okay, so what I want to do is basically talk about subproblems as subtrees. So what I want to focus on is this subproblem here. So if I pick a vertex V, I want to look at the subtree that is rooted at V. And this is basically well defined once you fix a root, right? So this is essentially all the descendants of V with respect to this particular root. So let's ask for the size of a maximum independent set in T sub V, which is the notation for the subtree that is rooted at V, right? And that's essentially going to be my DP table. So now the table is not really a table, it has taken on the form of a tree essentially. So you have the tree, and at every node of the tree, what we are going to do is try and store this value, which is the size of the largest independent set when you look downwards from wherever you're standing, right? And again, let's quickly go through our checklist. Do these subproblems help us get to our final answer? Well, take a minute to think about what should I write here to get my final answer. So if you look at the subtree that is rooted at the root, that is the entire tree. So T sub R is T. So if I basically plugged in the root vertex here, I would essentially have my answer. So I can compute my final answer based on these subproblems. So if I can solve these subproblems, I'm definitely in business. And what would be a natural choice for base cases? Well, a natural choice for a base case would be a vertex whose subtree is empty, so you don't have to go any further down. So such vertices in the context of trees are called leaves. These are basically the pendant vertices in the tree. So essentially you start from the root and go further down in the tree for as long as you can until you get stuck. And when you get stuck is when you realize you've hit a leaf, because there's nowhere further down to go. Each leaf in the tree basically gives you a base case, because the answer for V, if V is a leaf, is simply going to be the weight of V itself, because in that tiny world, you're basically constraining yourself to a subproblem of size 1. It's a company that has only one employee, and whatever fun factor that employee has is what you'll have to live with, because you don't really have much of a choice here, right? So that's going to be your base cases. So now that we know how to kickstart our recursion, which we haven't specified yet, but we know how to get it started if we did have a recurrence, we know that at the top we are going to get to our final answer. So now let's fill in the gap in between, which is to say, let's come up with the recurrence that would lead us to the final solution. So if I want to think about, I'm at a general place in this tree and I'm at a vertex V, and I'm looking at the subtree that is rooted at V, and of course there's, the rest of the instance is further up here, but my focus is on this subtree. So when we were working with arrays earlier, we were working with subarrays. This is kind of similar to that, except we are focused on a subtree instead of a subarray. That's all, right? So as before, like when we did longest increasing subsequence, we were sitting at the border and asking ourselves, well, does the ith element, participate or not? That's the sort of question that we want to ask ourselves here as well. So for the optimal solution in this subtree, what we don't know is it going to pick the vertex V or not, right? So is there an optimal solution that contains the vertex V, or does every optimal solution choose to ignore the vertex V? We don't know the answer to this question, but we can find out once again by trying all possibilities. So what do you think happens when the optimal solution does not contain the vertex V? So if every optimal solution chooses to ignore the vertex V, then essentially what's happening is you can think of your party as being the union of all the parties that come from all the subtrees that are rooted at the children of V. So let's say the children of V are V1 and so on up to some VL, and I basically look at the best parties that I can form in these subtrees and I just put them together, and that's going to be a valid party, a valid optimal choice under the assumption that V is not being invited. And why is this assumption important? Because some of these parties may have actually invited one of the children of V, and I want to be sure that that's actually not going to be a problem. So when V is not a part of any optimal solution, then combining the optimal solutions from the children would give us a good picture of what our best option looks like. On the other hand, suppose V is in fact invited to the party by some optimal solution. How can we discover this optimal solution through the DP table? Well, if V is in fact invited, then we know that all of its children are not invited, right? So now we do the same thing, except we go to the grandchildren, right? So we find the optimal parties from the subtrees that are rooted at the children of V1, at the children of V2, and so on up to the children of VL. Okay, so we take all of those and combine them, and we combine that also with the weight of V, and that's what's going to give us our final answer. So let me recap everything that I just said by writing down what the recurrence should be. So this value is going to be the better of two options. Our first option is going to be that V is not invited. In this case, we are essentially looking at the sum over I going from 1 to L, MIS of VI. That's our first option, and the second option would be that V is invited. And in this case, we know that none of its children are invited, because that would again basically violate the independence condition. So what's our answer here? Well, we're going to go over all the children and then go to their children. So let me just say I want to sum over W being a child of VI. and I'm going to look at the MIS of W. That's what we have here. And the better of the two options, because we don't know if V is invited or not. This we don't know up front. So we're basically going to try out both scenarios, get into these two parallel universes, use recursion magic to figure out what would happen in either of them, and then pick the better of the two options, right? And once again, if you want to convince yourself of the correctness, let's quickly think about the achievability and the optimality. Whatever this recurrence gives us, I want to argue that that's actually achievable. Well, that's because, again, by the induction hypothesis, these fellows here are doing their job. They will give you these invitee lists with the promised fun factor, whatever this is. So if MIS of V1 is 10, that means the induction hypothesis is reassuring us that in this subtree here, there is indeed a collection of people that we can invite whose total fun factor is going to be 10, and it's a valid collection. So we rely on the induction hypothesis to give us all of these smaller subparties, and of course we can then combine it with V as appropriate. And in fact, I do have to make a correction here to the recurrence, and some of you may have caught it when I was explaining, but just as we experienced with one of our previous examples, what we have done here is forgotten to include the contribution of V. So when V is invited, of course, V brings in their fun factor to the party. So we need to fix this recurrence by adding the weight of V in there. But once we have done that, we see that the induction hypothesis guarantees us the existence of all the smaller parties, and since V is not invited in the first case, we can just combine the parties without worrying about conflicts with V, and we have a valid party. In the second case, we want to include V, we want to invite V, and that's what gives us this portion of our fun factor. And the rest of the subparties that we get don't conflict with V because they're coming from the subtrees of the grandchildren. We have explicitly avoided all the conflicts that we may have with its children, right? So that is the argument for why what we are promising in this recurrence is actually something that we can achieve. Now, on the other hand, why is this optimal? Well, somebody comes to you and gives you an optimal solution, says this is the best that we can do. You look at their solution, check if V was invited or not, and depending on whether V was invited or not, you can go deeper into one of these branches and essentially once again rely on the induction hypothesis to compete with whatever optimal solution comes up for comparison. Okay, so that's again a sketch of how you would do the formal proof. We have argued all of the other elements. We know that the base cases are at the leaves, and we know that we just have to return MIS of R once we have done all of our computations. And the order of computation here is just going from leaves upwards towards the root. So in the first round, you're going to compute the values at the leaves, and then you'll go to everybody who is a node that only has leaf children, and you'll be able to compute those. And you just keep going until you have covered everything. So that's again a slightly non-trivial implementation, especially if you have not implemented DP on trees before. I think it's a fun challenge problem. Once again, watch out for pointers to problems that you can implement optionally in the course notes. There are links to things that you can try out on platforms like Codeforces if you feel like doing that. But even if you have a solid theoretical understanding of what's going on here, I think that's good enough for you to get started with the official graded and practice assignments, and I hope you have fun with those. I look forward to discussing them with you, and I'll see you back next week when we will talk about flows in graphs. Until then, see you next time.